We would now like to analyze a driven RC circuit. So in this circuit, let's remind ourselves that our resistor is at the top and the capacitor is down here at the bottom. And there we have our voltage source. So we're describing the circuit with a time-varying voltage source. So we have V naught e to the I omega t. There's the oscillating part. And if we want to see that source on our circuit, let's now introduce the voltage. And that's in blue. And we've chosen our t equals 0 such that the voltage is 0 at t equals 0. And when we run this, you can see that we have a oscillating voltage in time. Now our problem is to solve for the current in this circuit. And we write the current, I of t, is equal to an amplitude, the same sinusoidal phase factor, but we have a phase shift. And our goal is to find the amplitude and the phase. Now, when we introduce the current here in green, you can see that the current is peaking in time before the voltage. And when we run these, first the current peaks and then the voltage peaks. So here we say the current is leading the voltage or the voltage is lagging the current. Now let's solve for this by introducing our complex impedance. So we know that for two elements, the resistor and the capacitor that are in series, that the impedance adds, and the impedance of the capacitor was minus I over omega c, and the resistor R. And so right away, we can write down the amplitude of the complex number here as real part squared plus the imaginary part squared to the 1/2. And the phase, we'll write this phase as delta, is equal to the inverse tangent of the imaginary part over the real part. The imaginary part is negative 1 over omega c. The real part is r. So that's minus 1 over omega c times r. Now, the way we can solve for I naught and the phase is that we write the voltage equals the complex impedance times the current. And so that equation becomes V naught e to the I omega t equals the amplitude of the impedance, which we wrote down. There is the phase of the impedance. And we have I naught. We have the oscillatory part of the current and the phase of the current. And so you can see that the oscillatory parts will cancel when we divide through by them. And the real part of this equation has to be equal, and the imaginary part of the equation has to be equal. The imaginary parts are represented by the phase, and the real parts are by these amplitudes. And so I naught is simply the potential V naught amplitude of the voltage over that amplitude of the impedance. And so right away, we write r squared plus 1 over omega c squared to the 1/2. And when we want to write the phase, now in order for the phases to cancel, e to the I delta times e to the minus I phi has to be equal to 1. E to the 0 is equal to 1, and that says that delta is equal to phi because then e to the I phi times e to the minus I phi is 0. Let's just remind ourselves that e to the a, e to the b is equal to a e to the a plus b. And so we see that our phase is equal to delta, which is equal to the inverse tangent of minus 1 over omega c r. Now, let's look at some special cases here. Let's first look at the case where r equals 0. So then we have a pure capacitor. And when we set r equal to 0, now I may have to adjust amplitudes. The amplitude grows. What happened was, let's look at that again. Notice that the green is the current, and when we set R equal to 0, the phase is getting bigger and bigger, and the range of the phase here is minus pi over 2 for the pure capacitive circuit, 0. And so when we set R equal to 0, what we have is not a surprise that the phase is minus pi over 2. And now this is a pure capacitive element. You can see that the current is leading the voltage by a phase shift of pi over 2. Now, we could do a lot of different cases. We could make C very large or omega small and large. You can do this as exercises for yourself. Let's just look at one case where omega becomes very large. Now, our equation shows us that if omega goes to infinity, then we're basically saying that the capacitor is not contributing at all, and it's just a pure resistor where the current is V0 over R. Here in our simulation, but notice that as omega gets bigger, this term here gets smaller, and so the amplitude of the current should increase as omega gets larger. For small values of omega, this term contributes. The denominator is big, current is small. As we increase the value of omega, this term becomes less and less important until the limit, when this term makes no contribution, is just V0 over R, a pure resistor. So as we slowly increase omega, you can see that the amplitude of the current is growing. And this is as large as our omega becomes. Conversely, if we decreased omega and omega became smaller, the amplitude of the current would decrease. So you can play around with this mathlet that was developed by Haynes Miller in the math department at MIT and see what happens when you change the parameters. You can increase C, decrease C. You can increase R, decrease R. We can raise R, decrease it, and then see what happens and get some intuition for this driven RC circuit.